All right. So we're picking up here on, we talked about the Coriolis force, and we're just going to review some rules about the Coriolis force. Yes?
I had a question on your previous slide. You had one of the questions due on chapters.
It's always whenever we finish it in lecture. So I will post on my Twitter feed, or you have to be here in class to know that since we're going to finish, we don't have any more slides. So we're definitely going to get through this one. So this will be due the Monday after spring break.
Okay, that's...
I lose track of which chapter we're on. Are we on 6?
Yeah, we're on 6. Yeah.
So 6 will be due. So that's why I look it up and I post it on Twitter because I have to concentrate. I'm like, I don't know. So.
I just don't get on Twitter.
Well, then you have to be in class, I guess. So
I'm
you are.
Here.
I know.
You know, I don't get on Twitter either, but all you have to do is go on.
Yeah, it's a website,
e-college.
and I gave you that site in my. You don't even have to go on Twitter. If
Or
you have
just go to
internet,
the
you can.
e-college on the blog.
So,
you can click on
yeah,
that and it's right there.
I
That's how got
try.
to it.
The reason I've gone to that.
Simple to ask a question too.
Yeah, if you're here, but yes, and you are here. But a lot of students aren't here, and then they'd ask, and I'm like, I don't know. Let's go check my Twitter feed because I don't know. All my semesters start to run together. I think that's the nature of teaching. Sometimes it all just is a blur. But, all right, so I have Friday here. Actually, we spent some time on Wednesday, and I get my days mixed up, but we spent some time on Wednesday talking about this Coriolis force. And remember, this actually, it's an apparent deflection caused because the Earth is spinning. So basically, anything that leaves the Earth's surface, the Earth spins underneath it, and it looks like its trajectory has been deflected. Okay, so these are things that you're going to want to know. Here in a minute, you're going to see some some angles drawn in with regard to the CF. Okay, so it's going to go at a right angle relative to the direction of motion of the air or the wind. Okay, we said actually on Wednesday we talked about how basically it's strongest at upper latitudes, and near the equator it's basically 0. Okay. We said in the northern hemisphere it is deflection to the right, and I hate to keep harping, but I did post on my Twitter feed this whole thing where people think you can look at how the water spins down your toilet to know which hemisphere you're in. That is a myth. And so actually, don't believe me, ask the experts on the internet. So in the northern hemisphere, large bodies of moving air or objects, actually, you will see the deflection to the right. In the southern hemisphere, it is deflection to the left. Okay, and the faster it's going, the more the deflection, and the longer it's occurring, the more the deflection. So that's why the toilet bowl doesn't have the distance, really, to kind of have a twist. Okay, and whenever we talk about the Coriolis force, it only alters the direction, not the speed. Okay, so there were 3 things that actually in this chapter we said affects wind. We said the pressure gradient force creates it, the differences in pressures. We said the Coriolis force kind of deflects it to the right in the northern hemisphere, to the left in the southern hemisphere. This third force actually is the force of friction, otherwise known as FF. And we're all kind of familiar with the force of friction. Basically, as you kind of drag your feet on the carpet, you know, you're basically, depending upon how much weight you put on your foot, you have different amounts of friction, okay? And dragging it on linoleum is different than dragging it on carpet. So, not so surprising then, if we look at this little figure down here, okay, basically we have wind that really wants to flow. This little word, I like the word aloft. This is flow aloft at upper elevations. The closer the flow is to the Earth's surface, guess what? It has more drag, has more friction. So if we kind of think of the wind flowing in layers, okay, it basically gets slower and slower when it gets near the Earth's surface because of friction. So this actually, is it this slide? Yeah. I think this is so interesting. I chased this down a few years ago. Basically, as you go up in the troposphere, I'll put T for troposphere, the winds get faster and faster. Okay? When you cross from the troposphere into the stratosphere, actually the winds are going to get slower. Okay? The winds will begin getting slower into the stratosphere because of your pressure gradient force isn't as strong. And I'll have to talk about the pressure gradient force coming up. But
jet streams in the troposphere too.
the jet stream is in the troposphere, yes. Yep. Okay. So, winds if you guys want something to do, aside from getting your Chapter 6, apparently, Chapter 6 homework's going to be due the Monday after spring break. If you want something constructive in this class to do, you might want to take a look and read Chapter 7. And read Chapter 6 if you haven't, and it'll kind of reinforce what we've talked about. But Chapter 7 talks a lot about these kind of surface winds, and actually also winds going, and one of the things I need to do is try to convince you that there is a difference in winds here at the surface and winds, upper winds. They're just different. But the cool thing about upper winds, and we're going to have a few slides talking about them, is basically they generally flow directly from the west to the east in upper winds. Okay? And so we know that those upper winds, the only reason they can blow is because there must be a reason to blow a high and a low pressure. Okay? But I'm going to show you how that high and low pressure is not west and east. That high and low pressure actually is a high pressure over the equator and a low pressure over the poles. You're like, dude, how did you get? I'll grab my. I'll grab the. Mrs. Snipes, you told me that air will move from high. Okay, we have high pressure here, generally over the equator, and a low pressure here. So that would go like this, right? Okay. So why does not go like this? Well, on the next few slides, I'm going to convince you that basically we said it's veers to the right. Okay. So if it's supposed to go like this, veers it to the right. Guess what? That's where we have that upper level wind. Okay, that's westerly. So that's it. Coriolis force basically does its thing. Okay, at upper elevations. Oh my goodness. So at upper elevations, kind of these straight winds, again, these are upper elevations. I'm excited about the next chapter because we kind of, well, even this chapter we talk about kind of some swirly winds down here. But these straight upper level winds, those are called geostrophic winds. Okay, so geostrophic winds.
Where? I was trying to.
Oh, right here.
Okay.
The ones in upper elevation, the upper level westerlies. But don't really call them westerlies because actually we have a band of westerlies here that goes, we have a band of easterlies, westerlies, and actually easterlies that are on the Earth's surface. These are upper level westerly winds. And the ones that go parallel to the lines of latitude are geostrophic winds. So here we go. I'll just kind of put this whole thing up here. So I mentioned the, oops, let me go back. Oh, go back one more. Okay, so think of it this way. Let me go ahead, and it's not really the equator, but, oh, that isn't what I want to do. It's thinking. Let me go ahead and draw in, like if this is 0 latitude, it's not really. 0 degrees, like that's the equator, and I'll go ahead and put 90 degrees up here. It's not really, but just for kicks. I told you at upper elevations we have a high pressure over the equator, and we have a low pressure at the poles. Okay, so that's kind of orienting yourself. So that's that wind, that air that wants to move this way, but it's going to be deflected. And once it gets finally kind of at a right angle, basically to what we call the pressure gradient force, it's not going to twist anymore. It has a groove. That's geostrophic wind. Okay, and that's what you're seeing here. That purple one, geostrophic wind. This starting out here, the Coriolis force still needs to act on it. Once it's going at right angles to the pressure gradient force, it's done twisting, basically, is the way I think it. Okay? So, all right. Maybe. It did not want to, it's ready for spring break, I think. Yes. Okay. So what we're looking at here, it looks like those isobars, where we said those the lines connect locations with the same pressure, but it's not quite that. Basically, this is called an isobaric map, where somebody said, let's go ahead and write in the elevation. So these are elevations. So this is, I think it's in feet. This is 5,730 feet. This is 5,310 feet. Okay, those are elevations to reach 500 millibars. It's an isobaric map. Okay, so those are down. I don't know if you guys remember, but one thing we covered in this chapter was, in general, sea level is what?
2013.
Yep, 1,013. Oops, a little bit of dyslexia there. 1,013 millibars. Yep. So that's sea level. So this is all just saying how high do you need to go up in order to jack it down basically in half. So those are called iso heights. Like this slide says, though, you can go ahead and kind of use them kind of similar to isobars, in that the tighter they are, and actually we talked about this before, the tighter they are, they're really tight here. Okay, then we figure we're going to experience a stronger or a more drastic change in pressure, so we're going to have stronger winds. So you can see kind of the more flags there means stronger wind. Here they're kind of loose, okay? The wind is not as great. All right, the other thing I want to mention about this map is, and this will come up again, okay? Well, first off, we're going to talk here in a minute about these H's and L's again. Of course, the H stands for high pressure, okay, and the L stands for low pressure. The other thing is, can you kind of see this has like a wave to it, okay? Kind of the waviness of the flow. Actually, later on in after break, we're going to call those Rossby waves. That's actually in the next chapter, but I'll go ahead and kind of introduce you to those waviness. The other thing what I kept trying to say is the ridges are actually associated with high pressures, so kind of this, and I like it because it almost looks like a ridge, right? Okay, and troughs, this is a trough, are associated with low pressures. So if we have Rossby waves kind of in place, we kind of have alternating high and low pressures. Okay. So geostrophic wind, okay, and geostrophic flow to me are very similar. The geostrophic wind we said was kind of the geostrophic wind we said is kind of that straight wind that basically goes between isobars at upper elevations. Okay, and it actually definitely is a westerly wind from the east to the west. Okay, geostrophic wind would be kind of like the Rossby waves. It's kind of just the general pattern. It's not always straight. Then I'm not sure if this textbook that we're using this semester talks about this, but there is this thing called Bayes-Ballott's law. And this will make more sense when we talk about around highs and low pressures, maybe how does wind flow. But basically, if you find the wind, okay, find the wind, the direction the wind's blowing, we can look at the flag out here, and it is blowing a little bit. Oh, yeah, it's an easterly wind. Isn't that exciting? Okay, so it's flowing from the east, so you put out your left hand, and it's two L's. You put out your left hand, and there actually is a low pressure there. Excuse me, low pressure will be on your left, yeah. Okay, with the wind at your back. Oh, my goodness. Those people, I hope that doesn't drain their battery.
They kind of deserve it.
I feel bad. They might be in class taking a test or something. So, geostrophic winds are kind of those upper level winds. Gradient winds, there's a similarity here, but gradient winds are also winds that are flowing between isobars, but it's curvy because the isobars are curving. Case in point, we actually here, I think, if not, we will be. But when you look on a weather map, oftentimes, and you're looking for the isobars, a lot of times it'll look like a bullseye. Okay? And actually, usually your lows will have, and these things that I'm drawing are isobars. So your lows, and actually the example we have coming up, your lows have a lot tighter pressure gradient. So that means that you don't have to go very far before you get that change in pressure. That means you can have stronger wind. So actually here on the next slide, or I think it's coming up soon, we're going to talk about how winds actually go around. And actually they're going to go clockwise here, and they're going to go counterclockwise here. Those winds are gradient winds.
Now, I might be going off subject here, and I apologize. Is these what help cause like tornadoes and stuff like that when they get together or clash?
No, the thing that from tornado science is they're still working on it, right? They're chasing tornadoes because they're so short-lived and everything. But tornadoes actually are a direct result of your cumulonimbus, what's going on in your storm cloud.
But doesn't the high and low pressure? And
not really. It's a front usually. It's usually a front. The cold front usually will give you your lifting mechanism to give you your storm clouds, and from your storm clouds, it's that updraft and stuff that actually gives you your tornado underneath that.
Okay.
So yeah, usually these highs and lows don't do it. Usually it's a frontal lifting sort of thing.
I didn't know they could be involved in
Yeah, not usually. So I love these two slides. These are exciting. So these actually talk you through these two. Okay, so let's consider this one. So if you want to put a star on this slide, you can, because I definitely have questions over this one. The name of this system is a cyclone. Okay, what? Not, it doesn't have to be here. Like we can have L's anywhere. So if it was somewhere else, it wouldn't be a mid-latitude cyclone. But it's called a cyclone.
To keep you from thinking about a tropical cyclone?
The mid-latitude cyclones in Chapter 9, we're going to talk about. Those actually do start out as this, but I don't think all lows progress into mid-latitude cyclones. I think, anyway. I usually reserve that term for storms. So if it's a low pressure, and if those black things are isobars, guess what? We should, as we step out from those isobars, the pressure should be getting higher and higher. So check this out. 104, 108, okay, 112. Those are the isobars getting higher pressure. That makes sense, right? All right. Then the other thing we talked about, see that little blue thing here? This actually is going to be your wind. Okay? If this is low, then this is relatively high. So wind is going to go from high to low. So here we go, right? And though we said it's going to go this way, but it's going to be deflected to the right. So here we go. Can you see your little blue line getting deflected because of the Coriolis force? But once it gets in the groove between those isobars, it's gradient wind, and it's going to stay there. So basically, that's why you see it kind of in the groove.
Oh, isn't the tighter the isobars, the faster the wind?
Right. The tighter the isobars, the faster the wind. Exactly. So this is a cyclone, and these are the characteristics. I said go ahead and mark this one. Okay. So I tried to explain with the blue arrows, with the movement of wind and the Coriolis force and all that, actually around your lows, and we'll start to try to kind of look at that a little bit, around your lows, expect for clockwise motion. Counterclockwise motion. Final answer.
I didn't put counterclockwise.
Yeah, counterclockwise. Counterclockwise around the low in our hemisphere. Okay, clockwise around the high. Every once in a while I get those mixed up. The other thing, so we call the flow cyclonic. The type of flow is cyclonic. It's out and out called a cyclone. Notice a few slides ago we said it's associated with those troughs. And so actually, let's see if I could do this on here. I could go ahead and draw in my trough like here. This is kind of my upper level wind. And actually here in a minute you're going to see that this is associated with a ridge. I've kind of mixed my blue is upper level and my black is lower level, basically. All right, one more thing. Okay, go ahead.
Because if you're moving this way, that'd be the wind, where the wind's blowing.
Right.
Let's see, but the high is moving counterclockwise.
Okay, so blue is upper.
Yeah.
With an exclamation point. Okay, and black is lower.
Level winds as far as the
Mm-hmm.
Yeah, okay, I see.
So I have just mixed my apples and oranges.
surface winds and upper.
Yeah, surface is the word, yeah. This is
Okay,
surface.
that's clockwise, one's counterclockwise.
Yeah, and I would say though, even though I've kind of mixed my surface and my upper level, that's kind of what meteorology does.
Right.
That's kind of what weather does.
Well,
It
kind
kind
of
of is a
makes sense.
three-dimension thing. Yeah.
It makes sense that even in the upper atmosphere that there would be sort of a dip in the gradient where a low would be.
It's not all. Sometimes it's like zonal flow and it's like there, but yeah, it does, and then you don't get these on the surface.
Right.
But the last bit there, are we okay with this? That actually, even though the air is moving counterclockwise, right? In general, we do have a convergence going on here. We basically, from high to low, it's kind of like the deal where you throw candy out anywhere. You break the piñata and everybody rolls, okay? Convergence. Right. So, now let's talk about the other one. Anticyclones. Okay, anticyclones, and it's a surface weather system. And this kind of goes to what Joe said. Basically, if it's an H, an anticyclone, or an L, a cyclone, it kind of takes over. You've seen sometimes they take over multiple states. It's like a weather system in place. Okay, so if that is a high, then when we talk about the isobars, they should be getting smaller. So it looks like a bullseye, so we go from getting lower pressure. So we go from 1024 to 1020 to 1016, so we're stepping down. So in this case, to kind of show its start, I'm going to have to start it there and go outward, aren't I? Okay, so look for the little blue thing, okay? So it's going to try to get out, but it's going to be deflected to the right, okay? And deflection to the right, that's what makes it go clockwise. I just think that is so cool. And that's your gradient wind. When it's in the groove between the isobars, that is your gradient wind.
Isn't it funny that because of its deflection to the right, the low pressure goes left, or goes counterclockwise, because it starts here and then it gets into that,
Yeah.
you know, that
The groove between
yeah.
the isobars?
So it automatically pulls it that way, but it happens the same way for the high,
Yeah.
even though they're both pulling it to the right.
I don't know if I've really thought of it like that, but that is interesting. Go back, right?
Yeah.
Sometimes I get a little carried away with my clicking.
We're fast.
Not that fast. And this whole bit about cyclone and anticyclone, it is so cool. And this is kind of what Autumn was talking about. Do you know, did I already say, if you look at the North Pole, what direction the Earth is spinning? Is it clockwise or counterclockwise? Yeah, 50-50 chance. It is counterclockwise. Very good.
I had to think about it. I was like, wait, is this
It
a
is
trick question?
I know. It is counterclockwise. So that's why actually the L's going counterclockwise, that's our cyclones. Because actually they're moving the same direction as in that hemisphere. So here's the deal. What if you look down the southern hemisphere? What direction is the Earth spinning? Clockwise. I know it's confusing.
It is confusing. It's,
So here,
it's like a trick.
it is trick. Here, is that counterclockwise?
Yeah.
Here,
It's clockwise.
clockwise. You're like, dude, I know. So here then the cyclones go clockwise in the southern hemisphere. So the L's are still are cyclones, but they go clockwise. But that's kind of how that goes. Okay, we already
So
said.
then the highest we go counterclockwise in the southern hemisphere. And everything is deflected to the left in the southern hemisphere.
It's just,
Right.
everything's just being
Right.
reversed.
Yes, yes, you're totally right. And so I'm going to add to this, actually, this is associated with ridges, and we said that this is upper elevations. I like that distinction. That's supposed to be elevations. Okay. Good. All right. So you have met cyclones and anticyclones. Frictional force, I don't have a lot to say. It's kind of the one that we know gives drag, basically. And it works opposite the direction of the wind. So if the wind's going this way, the frictional force is going this way. It's depicted by a purple arrow there. Okay, so that's the force of friction going opposite the direction of the wind.
What is the friction, at least the Earth, the planet, the mountains and stuff?
Yeah, exactly. The Earth, the planet, the mountains. Water, well, not water, but air moving over water has less friction than air moving over land.
Because water moves.
Yeah, because the water will move with it, and the water's more glassy, it's smoother. Anything rough gives you more friction. Yep. Yep. All right. So, speaking of, and I don't know if you just said about snow fences or whatever, but we put snow fences up there to basically give an obstacle for the wind, okay, to give more friction. Yeah, yeah. To give a place to have it drift at a certain location so it doesn't drift where you don't want it to. Yeah. I sure wish they had planted some trees there by the BP on you know, by Weaver, you know,
Weaver, I know
61.
you're-
That's
yeah.
terrible.
Oh,
I think they've done better this winter, but last winter, you know, you just had to slow it really down when you go there. Drifting is awful.
Well, they started building, did you see when they were plowing, they were putting that more snow on the one side too?
Okay.
Yeah, that's why you
Oh.
had that one drift.
Yeah,
You
all
know,
right.
what they were doing was building that.
A pop. Is that a break? A wind break?
Yeah.
Well, good for them. We'll have to pay attention to that. Yeah, I appreciate them out, so doing their thing.
Well, see, I come from a bigger community, and when they had a lot of snow, they would shut the road down and run dual bulldozers and push all the snow over to the direction of the wind.
Oh,
And see what
interesting.
happens, the snow goes over,
Mm-hmm.
and when you get it high enough over, it convects over to the other side of the road. And
That's a bad thing, isn't it?
no, because
That's
if
a
it,
good
if
thing,
it jumps,
okay.
if it jumps over the roads on the other side,
Okay. Yeah.
just like a ramp.
Okay. Well, hopefully we don't have any more snow this.
Come on, I want 6 more inches. 6 more inches.
Okay.
If we get 6 more inches, I will not be in school if you guys shoot me.
So here's the deal, and I didn't say it, but on the slide with the high, it said air is diverging. So here basically we have air converging. Okay, if air is converging, what this slide says is if it's kind of piling up there, eventually that low is not going to stay low very long. It's going to turn into a high. We could say a similar thing about our anticyclones. Basically, we have air leaving the area, and on your slide it said air is diverging. So it's diverging here and converging here. So this diverging means, you know, it's going to get thinner and thinner, and basically that high is going to turn into a low. So how do these weather systems sustain themselves for 5, 6, 7 days?
That's why I was just getting ready.
Yes, exactly. And
how does it sustain its wind? You know, because sometimes we have winds 12, 14 hours, high winds,
Yeah.
and especially at night, for the temperature changes and stuff like that. We have high.
yeah, I
high
agree.
winds.
And actually, a lot of times you can watch for days. You can watch these H's and highs, H's highs and L's lows, kind of go across the United States.
Migrate.
Yeah, migrate. They move. So here's the catch. Oh my goodness. Okay, and it involves actually. It involves, instead of kind of 2 dimensions at the surface, it involves the 3rd dimension from what's happening at upper elevations. So in order for that high to stay a high, basically it has to be fed. Okay, so basically a column of air, and you're going to see on the next slide, comes down to replenish that high.
The vortex.
There's a vortex at upper
Yeah.
elevations, yeah, to
Okay.
create that converging air to force it down to sustain the high. It's almost like they got together and made this happen. But and actually it's associated with your ridge. Your ridge actually helps this to happen. Okay. The other thing about high, if you want to, you know, these are anticyclones. And did I say that there should be clear skies a few slides ago under anticyclones instead of high? Okay, you can add that to it. Because usually your H's on the weather map, a lot of times it's clear.
skies.
Anti should be clear skies, exactly. So the high should be clear skies. So basically that air that's descending to go ahead and refuel our high, basically we said that as it goes lower, it's going to squeeze, it's going to get smaller. Instead of adiabatic cooling, it's going to be adiabatic warming. So actually this idea of air going down is one we're going to actually talk about in the next chapter too. When air is forced to go down, it actually will get smaller, the parcel of air, because the air's thicker, and it heats up, exactly. So the nice, dry, warm air is oftentimes associated with an anticyclone. So we have the 3rd dimension also helping with our surface lows. So the low pressure, though, actually, remember the deal is we have to, since the air is converging, we have to get rid of stuff. So in that case, we have a column of air ascending. And columns of air that ascend go up, we said, actually will get bigger, and what happens to temperature? It cools off. So if you want to, on the cyclone, yeah, you can actually write cloudy. Oftentimes, if there's enough moisture and it rose and cooled to the dew point temperature, for the cyclone, you're going to have clouds. For your L's, you're going to have clouds. So then we can have clouds.
Probably be the white puffy ones, something like that.
It varies, but yeah, there'll be the puffy ones, yeah, the cumulus ones, the one with vertical development, yep. Yeah, and this should be clear and warm, usually. And I don't know about temperature there, but very good. So this figure goes with what I just said. This figure goes with those words. So here we have, if we pick on the anticyclone.
Everything's opposite. So creepy.
Oh, if we pick on the anticyclone, can you kind of see basically the air coming down? Okay, to feed the high. Feed the pig. Yeah, to feed the high, yep. And then for the convergence at the low, we need air to go up, okay? And that's how it's sustained.
I know this is going to be, I'm asking probably done, but I've always noticed on the maps we've drawn and the maps you're seeing, there's always a high on the left and a low on the right.
Right. Not necessarily, you're right. Like you guys said, these things kind of migrate across the United States. So if we do have what we call meridional flow, if we have these like Rossby waves in place, basically it's going to alternating. Over here we'd have an L, and over here we'd have an H, and over here we'd have an L. And they just kind of like a conveyor belt go across the, kind of keep their form.
Okay.
Okay. Ideally, or in some cases. All right. So one more thing back here, since we've kind of been talking about it. Basically, in order to have this air go down to sustain the anticyclone, what we have at upper elevations is convergence to make that happen.
Because of diverging surface wind.
Right, and we have aloft, we have to sustain our low, to get rid of that stuff that's building up. We actually have divergence aloft to kind of, it's like a vacuum to kind of, yeah.
Interesting.
And you mentioned vorticity,
Yeah.
and actually I don't know if it's in this chapter, or I think it might be chapter 9 when we talk about vortices, but at upper elevation it has to do with kind of the angle, the kind of coming and going that create, the ridges create convergence aloft and troughs create divergence aloft. I know it's a lot, but okay. So other ways to get air moving vertically. So let's make sure we know this is vertical, right? So other ways to get air moving vertically. One happens possibly as this scenario is going from the sea towards the land. Basically, the sea is nice and glassy. The land has all got that friction going for it. So basically, there's a pile of it because that creates a high pressure and up it goes. Okay? So that's that one. This one is the other way, where basically it's going from land to the sea. And I keep drawing my westerly wind. So from land to the sea, this is nice and glassy over here. Okay, so basically it's going to have this friction, and then when it hits this, it's going to go whoo. Okay, so right there at the transition, it creates a low pressure actually. And so if this is a low, basically that'll create vertically coming down. And then we have this one. This one kind of reminds me of orographic lifting a little bit. Basically, when it scrunches up against a mountain, you create a high there. Okay. And then this one, actually, that would be on where the side of the mountain where the wind is blowing. That's the windward side. On the opposite side of the windward side is the leeward side. And actually, what we end up with there is kind of a squish sort of chunk of air there too, at the top of the mountain. So it's a high pressure at the top.
On the lows, we said that the air is ascending, right? Not descending?
Well, I think this is talking about a different, these don't have anything to do with cyclones or anticyclones. These are just other ways of getting air to move vertically. These are independent of cyclones or anticyclones.
Now you said the leeward was the opposite side of
where the wind's blowing, right?
So that's where that low pressure would be.
Actually, convergence means it creates a high pressure. So one of the things. Oh, go ahead.
No, I'm just the leeward side would be lower high pressure.
Leeward side at the top of the mountains, we have convergence.
Mm-hmm.
Okay, so actually that is a high pressure. We're not talking about these now. We're talking about something different.
Yeah.
Yeah.
Because it develops that.
Mm-hmm. And actually, Santa Ana winds, have you heard of Santa Ana winds? We're going to talk about some other winds that if you pick a mountain, basically, and put a high up there, okay, you're going to have, basically, it's going to vertically force, you know, and that's actually what we have with our Santa Ana winds. We have something on the leeward side that we call Chinook winds, and these are called Santa Anas on the westward side. So, very good. Oh, now we finish up with something kind of light. Okay, so if you say what direction is the wind blowing, that's kind of what these last slides finish up with. Of course, we're used to say it's a wind from the north, wind from the south, wind from the east or from the west, but actually you can convert those into degrees, where the north is 0, and then you kind of think of it going around, like if this is a compass. So we have 0, we have, this is north, this is east, this is south, and this is west. So that's kind of how that goes. So you can convert them to degrees if you wanted to, which I don't know why you'd want to. This is north, okay, east, south, and west.
Stale weeds.
What's that?
Never eat stale weeds.
Never eat stale Wheaties. Then some of you guys are fancy and have used these terms before. Okay, so for instance, if we pick on a wind from the north, you can say there's a wind from the north, or you can say there's a wind from the west, right? Or if it's between the two, you say that that wind is from the northwest. And if it's between north and northwest, we call that north-northwest. And if it's between northwest and west, we call that west-northwest. Now, I haven't yet included a question on my exam like this. I probably won't, but I think it's interesting. That's kind of how that all goes.
Like doing the weather log, they always tell you, and a lot of them are like east, southeast, or west, southwest.
Yeah, that's cool. They kind of pin it down. Mm-hmm. It's neat. All right. So sometimes this has made it to my test. We're going to talk about, in Chapter 7 after break, we're going to talk about prevailing winds. What a prevailing wind means is just generally where the wind comes from. So you guys would probably tell me we usually have a westerly wind. Right now we have an easterly wind, though, okay, which is kind of fun. Okay, so usually our surface, now these are surface winds. At upper elevations, everybody's got a westerly, okay, coming from the west, going to the east. But surface winds, that can kind of vary. So what they do is they make these wind roses, wind roses. And basically, for instance, this particular location, this time of year, it usually blows out of the northwest, okay? So that would be like the first one, okay? And then secondarily, we have the southwest. It looks like the segment, the length of the segment tells you how much it blows from that direction, okay? Yeah, so usually it's not out of the east because that's so small, that segment. That's how the wind roses go. So a place I want to visit, I do want to, yeah. I do want to. Australia. So what direction does the wind usually come if you're in Australia? What does it come from? Yep, exactly. That's where it usually comes from.
Why do you want to visit Australia?
I think it's going to be. I think it's going to be pretty and just interesting. I think I'd like to go out into the outback, carefully with a guide. What?
See the different cultures and stuff.
Yeah, the cultures would be cool. I guess the animals and the topography, I'd be more interested, but the culture would be cool. Yeah.
Meet Crocodile Dundee.
I think it would be neat. Be what?
I said meet Crocodile Dundee.
Crocodile Dundee.
You had to go there.
She said she needed a guide.
So if you don't have a windrose, to kind of tell you what the prevailing wind usually. By the way, windroses are just so general, you couldn't use them. But for practical purposes, yeah, these are practical, right? Kind of high tech, right? Wind vane. Pilots can quick and dirty tell, how inflated the sock is, means how fast it's blowing and the direction is. An aero vane, the fin will tell you direction, although that would be easier. But if you know your directions already. And then what happens is the propeller speed actually can be fed down electronically to somewhere else to tell you how fast the wind's blowing. So that would be a candidate for those ASOSs that we talked about. Kind of speaking about ASOSs, here we have a cup anemometer. I just think that is cool. And it's kind of like the propeller, but it has little cups to catch the wind, and it rotates, and then again, the rotational speed can be fed somewhere remotely to tell it. And here we have direction. So that's really an ASOS sort of thing. Yeah. All right. So just kind of finishing up. Another way to tell wind speed at upper elevations would be to watch the clouds. Actually, can we tell wind kind of if we watch clouds moving? We get a sense for it.
Sometimes you can
How fast
see
they're moving.
different levels of clouds moving in different directions.
Yes.
Sometimes, so that
If you
is
see,
cool.
That's neat.
if you see like, if you can tell in the clouds that you have fast wind and kind of slower wind, that's actually called wind shear, a difference in temperature, or not temperature, difference in speeds, and that actually is fodder for giving you a little bit of rotation, that if you do have a storm cloud, that actually can help your mesocyclone to create a tornado.
And besides having wind shear up there, you can have it down here too.
Right, yeah, if you have wind changing speed quickly. So, clouds are good. So I think all things considered, we'll just stop there for the day. This chapter will be due next Monday. But yeah, read your chapters. I think they're good.